material into the ovens, is that an issue of the ice getting stuck in the scoop or the ice getting stuck on the screen? And as a follow-up to that, is getting the icy material analyzed still the highest priority remaining for the TIGA instruments that are, or for the TIGA ovens that are left?
Okay. Until recently, the most difficult part of this problem was getting the icy soil out of the scoop itself. Originally, even before that, it was figuring out how to collect the stuff and rasp it and go through all of those difficulties. We had one attempt at delivery where the alignment was actually off and we missed the target and didn't actually get it onto the screen. Finally, just a few days ago, we did get some onto the screen, but it didn't go into the oven. We interpreted this as the soil, again, being very clumpy, and just some property of it makes it so it doesn't easily go into our ovens. And what we're doing now is at least from this particular location, we're not going to try to get that very difficult ice anymore, just with the idea that it's very, well, it's a hard thing to do and we're kind of running out of time. We're still keeping open the option of trying in another area called a cupboard, where we also see ice, and maybe it's ice of a little different kind. So that's still on our list of things we want to try in the future.
Okay, next up is Rachel Cortland from New Scientist.
Yeah, hi. I guess this is a question for Bill or Mike. I'm still a little unclear as to how this changes your sense of the geochemistry of Mars. In particular, do you think there was, as the poles of Mars moved, was there flowing water or standing water, ice that sublimated and created a giant puddle? Or, I mean, can you build up some sort of picture of what you think might have created these carbonates?
Okay, I'll begin and then pass it over to Mike, since he was making the more general comments, I guess, about the geochemistry. One of the things that does look different, at least to me, about the carbonates here is, as I mentioned, we're not in an area where we had flowing water, or at least there's no evidence of it. Doesn't mean it wasn't flowing there at some time. And assuming that we really do need liquid water to form these carbonates, which appears to be the case, then what this says is we might have had standing water some point in the past. It's possible that the ice that there is melted in situ and it stayed right in that spot, and the reactions happened there. It's really kind of all up in the air, and it's a little bit hard right now to say exactly how this might have happened and what the constraints are. And these are some of the things that, when Doug was referring to the data that's going to keep scientists occupied well into the future, this is clearly, I think, one of the questions we'll be trying to come to grips with over the next several years. But I'll pass it on to Mike for his comments.
Not much to add to Bill's comments about the carbonates, but I'll comment on his remark that it's all up in the air. The perchlorates, again, which change much about the chemistry as well as the behavior of water in the soils as they absorb the water and really keep the soil around them dry. The carbonates are formed up in, the perchlorate and that family of oxidants are formed up in the air, as they are on Earth. It's a result of photochemistry, materials that are formed with the assistance of sunlight, with the assistance of droplets of water, and they fall to the ground and mix in with the soil. So understanding the way the atmosphere and energetic processes in the atmosphere affect the soil and the way the soil interacts with the ice underneath it is a very, very interesting subject, and we really didn't expect it to go down that pathway with perchlorates. We've talked about oxidants on Mars, things like peroxide, for years. This suggests that there's really a different family and a different set of pathways that have to do with highly oxidized species, which we don't see so much on Earth, falling from the skies and interacting with the soil. So that's yet another chapter in the book.
And Ken Kramer from Spaceflight Magazine, you're up next on Phoenix Call.
Hi, thank you. Well, first, congratulations on a great mission. I have a question for Barry Goldstein. I'd like to know if you're going to use MRO to photograph Phoenix at all, perhaps one image or a series of images, as the carbon dioxide ice is being built up, and when you might do that. And also like to know from Peter, you've moved to headless rock. What have you learned, or what do you hope to learn? Thank you.
Well, we've obviously talked about that. It hasn't been formalized, but I'm sure that our request to do that will be honored. We still have some months to go before we start being encased in the CO2, but we have discussed that around the program office, and I'm sure it's going to be finalized. A lot of the details of when those images are taken have to do with the orbit of MRO when it's in the viewing site. So I'm sure we'll get those done over the course of the many months that we're basically frozen on the surface.
I can take the second part. We moved the rock called headless about 40 centimeters, and the purpose of that was to see, of course, what was under it. Now, if a lot of these materials are falling down from the sky onto the surface, they aren't likely to be falling under a rock, so there might be some differences just from the airfall material. And also, if there's any small films of water that are created in the warmer periods of Mars history, they tend to stick to the surfaces of rocks and produce salts. So we're hoping to find a different chemistry under the rock than next to the rock. So the rock has been moved. We see subtle color differences in the soil directly under the rock as compared to the soil around it, and we're quite anxious to take a look at this in some of our instruments. So hopefully in the next week or so we can get a sample into one of our instruments or several of our instruments, and then we want to look at the ice table under the rock to see if the rock warms more than the soil and actually depresses the ice table in response. And this has been modeled by one of our scientists, Mike Mellon at the University of Colorado, and he's really anxious to see if he can test out his theories on an actual Mars environment.
Okay, we normally limit these briefings to an hour, but we still have several questions on the line, so we're going to keep the lines open if you gentlemen don't mind and take some more questions. And next in the queue is Raphael Jaffe from Aerotech News.
Yes, my question is for Dr. Smith or the gentleman who's handling the Dr. Hecht. The soil layer is dry according to the probes that were stuck into it. However, there is definitely ice below it. How can that work?
Mike, do you want to take that?
Start, and then we can...
Okay, how can it work that the soil is dry above ice? Well, the temperatures change as you go below the surface, and ice is stable once it reaches, or at least the water vapor can freeze once it gets to the point where the temperature is the right value. And at this time of year, that's several inches below the surface. As you move above that, the temperatures are too warm for the ice to form, and it tends to be very dry. Now, the dryness of this soil is quite a mystery here, and we wonder if perhaps the perchlorate is also absorbing some of the water. And Mike, you've been studying the perchlorate. What do you think?
With a little bit of a